Hello, everyone.
So, welcome back to our MATLAB Onramp, and today I'm hosting instead of Andrea. So we're switching places. He's going to address your questions in the chat while I'm going through our presentation and the topics of today. So last time he explained to you the very basics of MATLAB, so how to create variables and work with them. Today we're addressing, let's say, a more visual topic, which is how to create figures and plotting, and then some, let's say, advanced, mm, in a way advanced features of MATLAB, which are the functions, which help us to automate and reduce the computing time of our scripts and algorithms. So, first of all, I want to start by showing you the winners of the um, let's say of the contest we created last time. So first place goes to Leonardo Agostini. So round of applauses. Andrea, you're not applauding.
Oh, yeah, you're right.
Okay. So Leonardo, you won a T-shirt, a coffee mug, and sunglasses from Matworks. And second place goes to Nicoletta Dalle Donne, uh, who's going to receive a T-shirt and a coffee mug. And then Andrea Montalti as third place will receive a T-shirt. So thank you all who took part in our, let's say, very little contest. And guys, get in touch with us, however you prefer, to see how we can give you your prizes. So I guess we should start. Oppa. Okay. So let's go with our MATLAB interface as usual. Actually, as you can see, I've got my MATLAB interface is a little bit different from what you saw last time, especially in terms of coloring. This is just a little fix I did in the preferences. So up here, I went to preferences into MATLAB to change the colors of my interface, which helped me, let's say, program for longer because my eyes get less fatigue while programming. Actually, this is an automated feature you can apply um, to your MATLAB, and in the following days we can share with you the very simple script to apply these color schemes to your command window, so you can program, let's say, for longer without a white background. Okay, let's go.
Please, sorry. Somebody in the comments says that the volume is quite low.
The volume is quite low. I should increase the capture then.
Okay.
Let's see. Let's see. Okay, it should be very better now. Okay, I'll even reduce it a little because I see the histogram that goes way up and saturates the gain. Okay, I think I fixed the volume of the microphone. If you still have any issues, please write into chat and don't worry about that. We'll address it as soon as possible. But now let's start with plotting with MATLAB. So last time we saw how to create variables and vectors of elements. This time I'm going to show actually to show how to show them to the user. So in this case, in this very simple example, I first of all create a vector called x1 using the linspace command. We saw the linspace command last time, which helps you create a vector of equally spaced elements from the first element to the last elements, and the third input, which is not mandatory, is the number of points you want to create in your vector, in your array. So for instance, we can also see this array, which is composed of 4 elements, as expected, that are equally spaced from 1 to 2 times pi. So what I want to do, for instance, is to apply this array to a built-in function, which is the sign function, which you saw last time. I'll try to use the correct terms to explain these procedures. Don't get scared by them. I feel like it is important that you start hearing these terms from the beginning, so you can become more proficient with MATLAB. So what I'm doing is I am passing this array to the built-in function to obtain the following output. So I pass an input to a function and I obtain the output of the function. So what happens is I am creating a vector, an array called epsilon1, which is once again composed of 4 terms, which is the number of elements I passed, and I can then plot my results. So the command to graph arrays is called plot. So let's say in a technical term we say we plot elements. We plot elements on MATLAB. So we simply pass 2 outputs, which are the element which goes on the x-axis and the element who goes on the y-axis to the built-in function plot. So plot x1 epsilon 1, and we obtain our plot. Let's say our figure. In this case, this figure is in line with our script because it's a live script. Otherwise, we would have a pop-up window called the figure with our plot. So we can't really see the sign function here. I'm sure some of you have already guessed why, and of course it's because of our let's say of our sampling of the function, because with 4 elements we can't really tell the shape of our function. So let's try something a little bit different. Let's increase the number of elements on our X array by a factor of 10. So let's go from 4 elements to 40 elements in the same interval. Once again, we pass our X vector, X array, to the same function, and we plot the results. What you obtain is a much finer plot of our function. To be more clear, I will go back and launch again my plot with 4 elements by adding a command to our plot function, and I'm going to say I don't want you to see lines that connect the points that I'm plotting. I only want to see the points themselves. So I insert a character, which is in this case lowercase o, which represents, let's say, which is interpreted by the plot command as the fact that I want to see only my points as plotted as dots. So what I see is the elements I'm plotting are actually these ones. Then MATLAB tries to interpolate them with a linear line and show me the plotted result. So the key fact I want you to take home about plotting is that the plotting itself is very much reliable on
relies a lot on the number of elements you give to the function. Same thing can happen here, for instance. As I can see, the points I'm actually plotting are these ones, but when I do a linear interpolation of them, what I obtain is a much smoother function. So if I increase the resolution even more, actually we can't really see that, but the single lines that connect the dots are much more finer for the function. So let's do something a little more elegant and add titles and labels to the axis. The simple commands to add them are xLabel, ylabel, and title. This function requires as input just the strings you want to give to the axis. So I can, for instance, I can write this is the x-axis under the apex, of course, because it's a string. And so this is the x-axis. Actually, what you're seeing is just me refreshing the live script. To apply modification, you should just click on Run section or Run. This depends on what kind of scripts you're working on. But still, actually, the result of plotting is a pop-up figure like this one, which you can work on that, but it's let's say a little bit more advanced, because you can go to tools and let's say change the picture as you want, but it's actually a little bit advanced. So maybe actually maybe we will see it during one of our next events. So we now know how to plot a function, to plot a figure. Now what if we want to make a more elegant presentation? For instance, we want to show different function in the same figure. This is done by using the command hold on. Hold on is simply a command to tell MATLAB not to overwrite the past plot with the new plot. So what I did here is I used the command close all to close all the figures I had opened. I created a new figure with the command figure, which if I run it in the command window will just create an empty window with actually nothing on that. So the command figure creates let's say a pop-up figure, and with the commands plot we can create the elements inside our figure. If we only use the plot command, the figure is automatically created. Unless we have used the hold on command, then all the plots are simply put on our last created figure. So apart from the command axis type, which I use to change the axis automatically of my figure, what I wanted to show you is the two figures from before, one over the other. So you can see how the resolution very much increases with the number of elements we use to evaluate our function in the X domain. So a little, let's say a little hint on the commands of plot. Actually, plot is a very much complicated command. My suggestion is always to run the docplot command. So just writing docplot to open up. If you run this in the window, in the command window, what you receive is the documentation of the plot command, which tells you all the possible syntaxes for your command, for your function, and then also examples how to create them. So to change the line style, to create different markers, we used this one previously, or even change the color of your elements in the figure. Let's say the useful property of the plot command is that it's a very simple command to implement, but it's very hard to master. So to obtain very elegant, very effective plots and figures, it actually requires a lot of practice. So let's move forward. This is actually what I just told you. So for instance, if I want to change the appearance of my line, I can create a dotted line, actually this is only a dotted line with let's say the superimposition of star markers. But if I use, for instance, like this, two elements, I can create not a dotted line but a segmented line. So this is another example on how to use the plot command. In this case, once again, I'm creating a vector, an array of elements from 0 to 10 of 50 elements, and I'm passing the x array to the sine function. Then I'm plotting it, holding on, passing the same array to the cosine function, and plotting it once again with a different style. So a dashed line with red circles. And then I'm holding off to avoid, let's say, errors in the next figures. And the result is actually this one. So two superimposed figures, one over the other, for instance, to appreciate the difference between them. In this case, it's just a difference in terms of phase, of offset. So, once again, if you want to, for instance, to avoid using lines at all, like in the example we saw before, we can just pass to the plot command the selected marker, like this, for instance, the lowercase o, so we can completely avoid creating an interpolation a linear interpolation between the points. Different markers are available, like the plus sign, the asterisk, the dot, or the X, and so on. Let's keep it as default. Okay, so some of you might have, might have wondered, but if you create a plot with many functions on it, of course we need to make, for instance, a presentation to our superiors about our amazing results of our research. We need, of course, to add a label, a legend to our plot, to let the final user appreciate what we've done. So in this case, the command is pretty straightforward. We just need to pass the command, use the function legend, and add as strings the text we want to show on our function. So let's see in a little bit more detail what is happening here. Once again, I'm creating a next array to evaluate my function. Then I'm passing my input array x on the function sine and cosine. I'm creating a figure, and then in only one command, I'm plotting the two functions by giving out the x-axis and the y-axis. So first plot, and then the second plot. A different way of doing this, I'm just commenting the plot, could be using plot x, y1, and then hold on, plot x, y2. and this works completely the same. I'll give you a little insight on the plot command. What happens is if I pass only one element to my function. What? Oh wait, I deleted the hold on. That wasn't meant to be. Okay. So what happened to the x-axis? The x-axis doesn't have any information now because we're only asking to plot the elements on the y-axis. So the x-axis automatically takes in the number of elements in the only passed argument to the function. So in this case, epsilon1 is a vector, is an array. We could see it in the workspace of 100 elements. So it's an array of one row and with 100 elements. So what is happening is automatically MATLAB takes as let's say as value for the x-axis 100 elements. So from 1 to 100. It actually automatically indexes the input array. So let's go back to our domain of -2 times pi to 2 times pi. So to add a legend, we just need to use the command legend and pass it a number of strings that is the same as the number of plots we have in our figure. So in this case, the first plot is epsilon y, which is the sine function. So what I wrote was, what I'm telling MATLAB is the first plot I created is the sine function. So I want to label it as for instance, sine of x. So the first string I pass to the command legend is the sine of x. This way, automatically, it is associated with the blue line. The second plot I created, is the cosine. So this way, the second input I give to the legend command is the label to associate to the second plot. Because, for instance, if I invert them, like cosine and sine, what happens is I'm obtaining the wrong result, because the first plot was the sine. So it was created as a blue line, and the second I can create as a red line, and they see that the blue line, which is the sine, is associated to the label cosine, which is actually inverted. So let's put it back to the correct form. And so you see the commands passed to the legend functions should not be put in, let's say, at random, but in a cardinal way as function of what functions you've plotted before. So I guess we've seen in a more or less complete way how to create plots and, let's say, master them on a basic level. Now let's see in a more technical way what is happening behind MATLAB when we create a plot. So the plot is actually an object inside of MATLAB. You can, if you want, let's say a more an approach more near to the programming thinking, you can of course create a plot and assign it to a variable. So before we've only wrote plot this, plot that. Now we're using the plot command, but assigning the result to a variable. For instance, in this case I called p. So what I created is a plot object, actually a line object, with different properties. So let's see if I can show all the properties. I can show all the properties, but surely on the command window. So what you are seeing now is all the properties that belong to our plot. This way we can actually, let's say, in an advanced way, if we want to change them and create more customized plots, we can. For instance, by changing the color of our plot by hand, instead of just saying red, green, or black plots. And also all the, let's say, all the styles, all the width. Actually, these are quite, let's say, advanced commands. So I suggest you take your time to explore them one by one. And we're just going to see some of them right now. So, for instance, if I want to access one of the properties of the object P, of the line object, which is my plot, I can just use the dot notation. So my object is P, and its property, for instance, is the property color. To access that property, and actually to change that property, I can directly create a new, let's say, a new variable and assign it to overwrite that property. So in this case, I'm telling MATLAB, okay, I want to create a string called red and assign it to the property color of the object P. So the value of p.color is then overwritten by my new input. So in this case, the color of the plot has changed. This time I've also changed the width of the line that defines my plot, and I put it equal to 1.5, while in original it was 1. So you can see you can access in a very direct and fast way the properties. Oh, that's so bad. The properties of your plot. My suggestion is always to avoid. What's happened? Okay. My suggestion is to, let's say, avoid using this approach to working with plots unless you really know what you're doing. So you take your screen, you open up your figure, you open up your documentation, and actually be very careful on what you're doing. But still, for advanced plotting, this is, I mean, for learning yourself and advanced plotting, this is the way to go, in my opinion. Then, we already saw how to create legends, exactly as what happens with the plot. Also, the legend can be associated with an object. In this case, I called my variable as LGD. So I just create my legend as I usually do and assign it to a new object. Now I got my object of which I can show all properties once again in the command window. Sorry, I didn't create it, so I need to create it. Very well. And I can show all of its properties. And so, actually, I can see a lot of information right here. I'm not even sure I know all of them, but for instance, we can change the edge color of our legend, the font size, and the font itself of our legend. For instance, change its position inside our figure, change its orientation, etc., etc. So it's very much useful for for a total control on your plots. Yeah, like in this case, I'm accessing the property font size of the legend and changing it. Then I can deactivate the property box, which is actually the rectangular box that contains the text. But I mean, these are all only examples of the of the control the user can have on plotting when using the properties of the object is created. Okay, so I guess right now we are able to create simple plots, and for those of you who are daring enough, you can also also know how to access all the, let's say, advanced properties of plotting to create very customized plots. Of course, as I said, it requires a little bit of experience, but I'm sure you can handle that. And now let's go to see let's say a cooler feature of MATLAB, which are plots in 3 dimensions. So for 2-dimensional plots, the command we used was plot. To plot in 3 dimensions, it's, let's say, very intuitive. You only need to use the command plot3, and let's see in this case how to create how to plot a parametric curve in 3 dimensions. So in this case, I'm creating let's say a domain array. In this case, I'm assuming my parametric curve is describing a motion in the 3-dimensional domain given by the time variable. So my base variable, my time in this case, is given by an equally spaced vector from -10 to 10 with 100 elements, and I'm just evaluating the time according to the parametric functions in the x, y, and z dimension. Then, in a very simple method, I just use the command plot3 and pass to it the variable x, y, and z, which are once again must be put in their natural order of x-axis, y-axis, and z-axis. And so, simply enough, I created my 3-dimensional plot. Actually, I think I can show you. Yes, I can open it up, which is what would happen if you created it with a normal script, not a live script. And then I should be able to rotate it to see what is happening. So you see, it's a very dynamical way of plotting, because it's 3-dimensional, and you can actually pan it as you prefer. I mean, change the view. So for parametric curves, actually, I won't go into more detail today, because it's actually very straightforward by knowing what's happening in the 2 dimensions. Of course, once again, the title, x label, and y label commands also work. Also adding the z label. The legend function can be used to add a legend to our figure. And actually, yes, also the way of associating the plot to an object can be used to actually delve deeper into its properties. On a more on a cooler note, we also have the surface plots, which are the ways that MATLAB allow you to plot not only parametric curves but also surfaces. So how can MATLAB evaluate function in a 2-dimensional domain? So what you need is actually only the vector containing the values for the x domain, for the y domain, and then with MATLAB you can evaluate that function on the z domain. So I'm showing you the first command, which is actually what you always need to input to create surface plots, which is the mesh grid command. So what is happening here is that I'm creating my x domain, I'm creating my y domain on which I want to evaluate my function, let's say my surface, and plot it three-dimensionally, and then I pass these vectors to the command mesh grid. Mesh grid is a command that based on the values I want to have on the x-axis and on the y-axis, it creates a matrix describing in 3 dimensions my, let's say, my base domain. So of course this is the first, for instance in this figure I would have my x domain and that then goes is scaled according to the y value to create actually a grid, yes, a grid of elements on which then I can evaluate my surface element by element. So what is happening here, for example, I want to plot the surface of the function sine of x plus the cosine of y. And so to plot a surface, I just need to use the surf command by passing the x domain, which is actually, you can see, a grid that contains different elements, the y vector, which both, of course, are the output, which both are the output of the mesh grid command by considering let's say the linear inputs, and as third command, as third element, I just need to pass the value of my surface, which then will be evaluated in all my grid, and the result in this case is this one. Of course, we can also go back a little to see that also in 3 dimensions the number of elements which we are considering to plot really affect the resolution of my final plot. So in this case, you can see I'm considering 20 elements on the y-axis and only should be two elements on the x-axis. And so of course the resolution is very different from what we've had originally, as you can see, 0.1. So so just to underline the importance of what we seen before, so that using finer elements as input to our plotting, all the plotting functions, is very important to obtain accurate graphs. But of course, our result is actually difficult to interpret because, of course, of its three-dimensional nature. So one simple way to define better what is happening to our function is to use the color bar command, which automatically adds a color bar to our function, so we can see the value of the single elements. Of course, once again, we could go to the documentation by writing .color bar to see that our very simple syntax that we used, of course, can be much more, let's say, much more advanced to see different. I mean, we can use it very much differently and obtain different results by passing different commands. Now, I won't spend a lot of time on this, but of course it's all in the documentation. You just need to explore it with the commands we've seen. So, going back to our seminar. Okay, so we've finished our introduction to the graphing prop commands of MATLAB and how to create and evaluate plots. Of course, it's a very short overview that's meant to let you understand how the figures of MATLAB work, how to create them, and to give you all the tools you can use to study more in depth these commands. Now, of course, if you have any questions, you can write them into chat, so Andrea can answer you, or pass them to me if they are too long to explain. But if there are no questions, I'm going forward with the Symbolic Math Toolbox, which is actually a toolbox of MATLAB. Toolboxes of MATLABs are like let's say add-ons to this, let's say, simple MATLAB software. They are free to download. Actually, I'll show you how to manage toolboxes by going to my MATLAB layout, and up here under add-ons you can get add-ons and manage add-ons. So these add-ons are actually the these add-ons are actually custom additions that users create for MATLAB, because you can always contribute to the creation of toolboxes, but most of them are toolboxes created by MathWorks. For instance, you can see here the statistics and machine learning toolbox. All these toolboxes add commands, built-in commands to your MATLAB library, as well as functions you can use to study better your problems. In fact, I wanted to talk to you about the Symbolic Math Toolbox, because it's a very useful tool for studying problems in a, let's say, in a general way, instead of using numerical arrays. So, how does it work? The Symbolic Math Toolbox allows you to create symbols you can use in equations and expressions. So in this case, I mean, it's a very simple example. I'm creating a symbol by using the sim command, a symbol that defines pi. Additionally, other than constants, I can also create custom variables. So for instance, I'm creating, with this command, I'm creating symbolic variables, which are A, B, C, and once again I'm recreating pi. So I'm launching these two lines of code, and if I go to see in my MATLAB GUI, in my workspace, I see that I've created some elements which are A, B, C, and pi. These, of course, this time are not numeric elements, because numeric elements are defined by a size, and for instance they're called double because they're floating point numbers, but they are objects. They are called sim. So if I double click on my symbolic object, I see its value, which I assign to A. But of course they are objects that cannot be used when working with numerical arrays. So we will see we need to work carefully when we're working with symbolic variables. So symbolic variables, inside their let's say let's call it environment, they can be changed by applying operations to them. In this case, I'm summing two elements. I'm summing two symbolic variables, and the result is automatic. So pi plus pi divided by 2 is 3 divided by 2 times pi. Otherwise, I can create symbols about numbers. I can, let's say, change the simple number 5 to a symbolic variable and work with it with the symbolic toolbox. So if I did, for instance, if I used the log 5 times plus log 5, what I obtain is a numeric result. So it's not so. As Andrea told you last time, numerical elements are called machine numbers. They're machine numbers because behind the user interface, MATLAB saves them in binary as a number of bits, and so they have a finite precision. For instance, if I calculate the square root of 2, I obtain a certain number of numbers that of course are finite in precision. But if I use the symbolic toolbox like sim square root of 2, what I obtain is actually a much more precise number, because it's not saved as a set of bits, but it's saved as a symbol, square root of 2. So going back to our initial result, so log 5 plus log 5, you can appreciate the difference between the results, because in the first case I'm obtaining the variable b, which is a symbolic object, and the result is much more clear to us than the single number that defines 2 times the logarithm of 5. So this actually helps us in working with complex functions, actually like a calculator. Yes, we could say that the symbolic toolbox is actually helps us bring MATLAB, let's say, near the effects of a calculator, to show us, let's say, to solve complex equations without obtaining an approximate numeric result. Because of course, when working with bits and machine numbers, there's always unfortunately an approximation which we actually can't overcome without, let's say, more powerful hardware. So let's go forward. In this case, I had saved A, my symbolic object A, as this element, and then B as 2 times the logarithm of 5. And I can work with symbolic variables and use them in mathematical expressions. So in this case, I can sum two different symbolic variables and obtain a complex result. Now, of course, I can create, as I did before, different symbolic variables with only one command. In this case, for instance, I'm saving different variables in an expression and saving it as a symbolic object parabola. And of course, I can see it's let's say it's a generic form. So A, B, and C are generic. Let's call them generic symbols, which of course later I can change with numeric variables. to evaluate my function in different ways. So, as I said, we can create expressions, but also we can create complex equations. How? Let's see it with the Euler Identity. In this case, I'm creating the symbols pi and the imaginary unit. And what I'm doing is I'm creating a variable, the symbolic object Euler, by assigning this equality. So this is better explained by reading it from the right to the left, as always in the programming world. So what I'm saying is, okay, I'm telling MATLAB that there is this expression, which is the Euler identity, and I'm telling MATLAB that this must be equal, so 2 times the equal sign, to assign an equality between different elements. This is equal to 0. Now, after I've written this, I want MATLAB to save it as the object Euler. So you read it from the right to the left. So create this element and assign it to this variable. So if I run these codes, what I obtain is the element called Euler, which is an equation by itself. So this actually we won't see today, unfortunately because of the restricted time we have. But with MATLAB we can create polynomials in a very simple way by only giving MATLAB the coefficients of the polynomial. So for instance, we can create a vector, a numeric vector with the elements, and then using the command poly to sim of the vector we just created, we can create polynomials automatically by using the coefficient with just input into MATLAB. So I know this may seem a lot right now, but just to give you a path of thought to follow, what we're doing is creating all the basics so we can solve automatically any kind of equation with MATLAB. So for instance, what we created like expressions and equations, we will later see how to solve them with MATLAB with the command solve by giving it the unknown of the expression. So going forward, we can also create piecewise functions, so our system of equations. For instance, in this case, I use the command piecewise to create a function, actually the function -1, not really a function, isn't it? Is it? Time x squared, for instance. Yes, so -x squared, which is valid for x minus when x is less than 0, and for instance 1 when x is greater than 0. So what I created here with this command is actually shown graphically here, and it's a system of 2 equations. So let's create a function, for instance. In this case, I'm telling MATLAB not only the symbolic element I'm going to use in the function, but also but only the name of the function. But by telling MATLAB that the function depends on x, MATLAB automatically sees the object x inside of MATLAB as a symbolic as a symbolic element to evaluate the function. So I create the symbolic object f of x, and I'm writing its value right here. So x to the fourth minus 2x to the third power, etc., etc. And then what I want to do is evaluate my function for a given value of x. So very simple, a very simple way how you would do it on paper. The result is obtained by typing in f of minus 5, for instance. Sorry. Or f of 5, f evaluated in pi. Oh no, sorry, this just changes the value of x with the symbolic object pi we created before. So, for instance, f evaluated in 10, in 0. So, of course, f evaluated in 0. All of these are 0 except for the offset from the origin, so 10. Another way of evaluating function can be the command feval, so function evaluation, by giving in the function we want to evaluate and the point where we want to evaluate our function. So, so for instance, spoiler ahead, if we want to evaluate the derivative of a function at a certain point in time, for instance, we can use MATLAB to differentiate our symbolic function, and then using the command feval we can evaluate the derivative in a point in particular, for instance, to find the slope in a particular point. So, how to solve equations with MATLAB? We've seen how to create expressions, how to create functions and evaluate them. Now let's see how to solve different equations. So in this case, I'm creating simple functions, actually simple expressions, like y1 and y2, and then I'm not really comparing them. I'm defining that the two must be equal, and I'm passing them to the command solve. So what I'm telling MATLAB is, okay, I have my functions, which are x plus 3 and 3 times x. I want them to be equal one to the other, and I want you to solve the equality. So, given that in these functions there's only one unknown, which is x, MATLAB automatically solves my system, my equation, for the known x, and obtain my result in a very straightforward way. So, if in another case we have more than one solution to our equations, like in this case, x to the fourth power equal 1. What happens is that by giving MATLAB the solve commands, the result is a vector of all the elements that solve the equation. This, of course, can be actually mathematically is completely correct, but in a physical way it can be not really useful, because we might have done some assumptions on our problem. So this is solved by using the assume command. So in this case, for instance, I'm using the assume command by telling MATLAB that x, which is the symbolic object in my equation, must be real. So of course I expect that the imaginary elements won't be seen in my results. To add other assumptions, I cannot use the assume command because it would overwrite my previous assumptions. I have to use the command assume also, which is let's say a follow-up command to the assume one. And so in this case I'm using assume also what? I want to assume that x not only is real but is also greater than 0. So assume also, and then we can check the current assumptions. because the assumptions are basically properties that I assign to my symbolic object. So I can check the assumptions on x, so assumptions of x, and the result is all the assumptions I've made on my variable. In this case, x is real and x is greater than 0. So if I once again run the solve command on the previous equation, what I obtain is not anymore an array of 4 elements, but the remaining element, which is the only one that satisfies the equation and all the assumptions I made on my variable. Okay, this actually is the same as before. So I'm creating a symbolic variable and I ask Matlab to solve this equation, obtaining 2 different results, because as I could assume, a second order equation has got 2 different roots. But if I assume that x must be greater than 0 and run again the solve command, I obtain only 1 root. Okay, so just for a brief in-depth analysis, we can see the common assumptions we can give to symbolic elements. This, of course, is still is always in the documentation if you want to study it better. But still, we can see that we can pass a lot of properties to the assume command. For instance, consider a real number, only even numbers, odd numbers, or also limit the domain from 0 to important command, which is subs. The subs commands allow you to substitute values into your equations. So in this case, I'm considering 2 possible symbols, which are x and x0. The subs command allows me to select an expression or an equation, select the object I want to substitute in my equation, and then what I want to put instead of my object. So in this case, in this equation, I'm changing x to x0 minus 1, and you can see the equation is automatically updated. More importantly, what if we want to evaluate our function in one point? We should be able, yes, to substitute a numerical value inside of our function. So this is another way of evaluating a function in one point. x0 minus 1, once again. Okay. Yeah, of course the same happens if I have more than one variable. So in this case I'm considering this expression, so cosine plus the sine minus the exponential of the different variables a, b, and 2 times c. So to change them with numerical values, or for instance with different symbolic variables, I need to define the vector containing the variables I want to change, the objects I want to change, and then let's say the numbers I want to substitute into my equation. So what is happening here? I'm evaluating my multivariable function in different points by assigning floating point numbers to my symbolic objects. Okay, so as I said, Matlab is not only limited to evaluating and solving simple equations, but it also can help us with calculus. So by doing different differentiation, integration, or or also by expanding our functions into, for instance, in Taylor series. The commands are pretty straightforward. So to differentiate a function, we just pass it to the command diff. So diff of a function, of a symbolic function, gives us the derivative of our function. By passing the differentiated function once again to the diff command, you obtain the second derivative of a function. Or in a more straightforward way, we can just use the diff command with two inputs, which are the function we want to differentiate and the number of times we want to differentiate it. So in this case, in line 125, I'm finding out the second derivative of the function sign with just one line of code. So of course now it's a very simple function, but even for if I have, for instance, difficult functions like plus the tan of x, for instance, of course it's very useful for very fast computation of derivatives of functions without the need to work with paper, basically. So if you're doing like scientific computations, you want to find, for instance, the Jacobian of a particular functions, this is the way to go because it's very much straightforward, and let's say it takes out the probability of error while working on paper. So yeah, this is actually what we just did. Yeah, of course, as I said, the Jacobian of a function. What if we have different variables in our function? Like in this case, we've got x, y, and z. If you have more than one variable, we need to define the variable of which we want to find the differentiation of the function. So in this case, for instance, I'm doing diff of the function I just called, according to x. So of course everything else is not considered, and I just obtain the derivative of 2 times x squared, which is 4x. And the same happens in y and z. So not only we can compute derivatives of functions, but also partial derivatives of functions, which can be quite complex in some cases. So also by considering the opposite of the differentiation, the opposite of the differentiation is the integral, of course, and MATLAB allows us to evaluate both the definite and the indefinite integrals. So by using the command int of a function, we can give the boundaries on which integrate to obtain a numerical value, or without giving it, we obtain the indefinite integral. So actually a very useful tool for obtaining complex integrals without the need to do them by hand. Also some peculiarities, for instance, the Taylor series of a function is obtaining by creating a function and passing it to the function to the command Taylor. So in this case I'm obtaining the Taylor expansion of this function. Or if you want to evaluate through a different expansion point, the expansion point can be given as a name value command. Name value commands or properties of a function are inputs that must be given out as a couple. So in many cases you will find commands that will require you, for instance, a string to define the property you want to change, and the value to assign to that property. So in this case, I'm considering the Taylor function and telling MATLAB to assign to the property expansion point of the Taylor command the point 2. And so, of course, obtain a different result than before. Also, in a very simple way, we won't spend much time on this because it's very straightforward. We can evaluate the limits by the command limit of a function by giving it the variable for which to evaluate the limit, the point of accumulation, and for instance the left or right limit. Of course, I use the tangent function to do this example because I can show you that the left limit and the right limit are different, and of course if they are different, let's say the global limit doesn't exist. So in this case the result is not a number. If you obtain the none result, the not a number result, you should always be careful because it's let's say an error. Actually not really an error, but the computation of MATLAB isn't really correct, so you can you should check back what you've done. Okay, going back to our plotting. Yes, I was told by Andrea to slow down a little bit. Of course, I will slow down a little bit. I was just trying to let's say avoid going out of time, but still we can try. So to plot using functions is done as you would do with the usual plot. Just the command changes, not from plot. I mean, you shouldn't use plot, but fplot. By using fplot and giving out a symbolic function or a function handle, which we'll see later, we can plot functions without even giving out the domain of the function because it's computed automatically. In this case, from -5 to 5, or we can give the domain, for instance, from -pi to pi, and the function is plotted automatically. I mean, what is happening behind the fplot command is that the function is evaluated in all the points from -pi to pi, and then plotted in our domain. Of course, if the function is found to have infinite values, the asymptotes are automatically plotted in the figure. Okay, this is actually another example of plotting symbolic functions. In this case, my function is square root of x, and I'm telling MATLAB, okay, f of x is a symbolic function, so take x as the input variable. So f of x is considered as the root of the square root of x, and if I pass fplot to f of x, it's automatically plotted. Of course, in this case, the function doesn't exist for x in the real domain. It doesn't exist for x less than 0, so the x domain is automatically adjusted from 0 to 5. Okay, the same can be done in 3 dimensions, of course, with the command fplot3. As you can see, it's very much straightforward to plot with functions. You usually just put an f before the plotting command. And of course we can plot also parametric functions in 3 dimensions. The same happens with the surface command. So with surf, we plot surfaces in the 3 dimensions. With fsurf, we plot in 3 dimensions the functions we've just created, so without the requirement of evaluating point by point the functions. So actually this part we've mostly seen last time about linear algebra. What I want to show you is that you can work with the symbolic toolbox to create matrices and vectors. So it's pretty much straightforward. Also to evaluate their product. I mean their row by column product. In this case, I'm considering a general matrix A, 2 by 2, a general array X of 2 times 1, and then I can compute the product between the two as B. So B is a symbolic class object, but its values are exactly the generic result of our product. So A1 x1 plus A3 times x2, which is the row by column operation on the matrix and the vector. Of course, in this case, it's pretty much straightforward because we got a 2 by 2 matrix. In case of higher order matrices, of course, this tool will be a lot more useful for computing the results. So, if we got a very complex matrix, we can just consider that of A to find the determinant of the matrix. So, in this case, of course, once again, it's a 2 by 2. It can be computed automatically in this case, but also for higher order matrices. Matrices can also be created automatically, by considering let's say the name of the elements we want to create and the dimension of the matrix we want to create. So in this case, we create a symbolic object of which the elements are called A, and the dimension of this object should be 2 times 4. So if I create a 4 times 4 or a 4 times 10, you can see the names, the matrix is created automatically and the names are assigned automatically. So of course this is very useful, for instance, if you want to solve a particular problem in a general way. If you want, for instance, to find the coefficients of the matrix. Okay, this is actually another example on how to solve linear systems with the symbolic toolbox by considering a known matrix with numeric elements, a vector of unknowns x1, x2, x3, and a known vector of elements of which the system is equal to. So I can create a symbolic variable, my system, which is equal to what? To the row by column product of A and X, which is equal to the known vector B. So in this case, I've created my complete matrix that describes the linear system, which of course is a symbolic array. We can see because we used the symbolic toolbox. We can extract the single equations, from our system. So I created the element my system, the array my system, so my system, the element 1 of my system, element 2, element 3, and save them as equations. So I can work with my equations, for instance, by summing, doing the product with a scalar of my equations, and actually change them as we prefer. So actually, what we do here is the Gauss-Jordan, actually to obtain the Gauss-Jordan elimination, which is actually, as you might remember from algebra, not really immediate to do for large matrices. So MATLAB comes into our help by giving us the ref command, which allows us to do it automatically. So we pass to the ref command our complete matrix, so the matrix, the incomplete matrix A and the known vector B, and what we obtain actually is the visually is the complete result we want. So x3 is equal to minus 1/3, x2 is equal to 0, and x1 is equal to 2. And of course, this is already a numerical result, so we can use it to work on MATLAB. But if you want to see it in a more elegant way, we can convert it to a symbol, to a symbolic class object, and show it as we prefer. So otherwise, other commands for matrices are linsolve, by giving the matrix and the vector of known elements. So in this case, I'm only working with numerical elements. So it works for both the symbolic toolbox and numerical, let's say, numerical elements. And also the command for the symbolic toolbox to solve, for instance, for the eigenvalues of a matrix. In this case, I'm working with a matrix, a known matrix of numeric elements. We know that the eigenvalues of a matrix are found by using by imposing the determinant of the system lambda times the identity matrix minus A equal to 0. So I can create my identity matrix of dimension 2 by using the command I. I2, which is literally the I matrix, identity matrix of dimension 2 times 2. Then I create my symbolic variable lambda and write and save as characteristic polynomial the determinant of lambda I minus A, which you can see actually lambda is already seen by MATLAB as the symbol lambda. So we can solve our characteristic polynomial by considering it equal to 0 and passing it to the command solve, and found the two eigenvalues of our matrix. Okay, this is just other exercises, but it doesn't add any theory to what we've seen right now. So this concludes our part on the plotting routines of MATLAB and on the symbolic math using MATLAB. And now we're going to address, let's say, the automation of programming with the functions. So let's change script and see how can we automate our scripts and algorithms by using functions. So if any of you have any experience with our other programming languages, you might find many similarities between how functions are defined in MATLAB and how they are defined in the other languages. Because of course, to work with a function, so to create a, let's call it a subroutine in our script, that subroutine must be defined or prototyped initially before being used in our scripts. So how do we define functions? To define functions, we can both define them as single files or at the end of our script. They are defined by using the keyword function and defining the outputs we want from our function, the name of the function we want to have, and then the inputs to give to our function. Let's see a direct example on we can create a simple function. For instance, we can use the keyword function to define what? A function called sum2, which takes as input x and the output is called y. Then inside the function we can do whatever we want. We can create different variables. For instance, z equals 4, plot zx dot, and then actually the only constraint inside of our function is the fact that the output, which must be given out from our function, must be present inside the definition of our function. So in this case, what happens is, when in my script I call for this function, so I just write, in this case, sum2 of anything I want, and that anything can be called as we prefer. The result, so the output of my function would be the value y evaluated on the basis of x. So when I call my function, this subroutine automatically gets into work, and so all the commands contained between the function keyword and the end keywords are executed, and the only output I have from my function is the value of y. So the most important part of creating functions is that when we launch these subroutines, they won't affect our workspace, and so it will keep clean. So we won't have to, let's say, work with a myriad of variables which we might not need to use during our script. So actually, I'll be very fast in describing let's say the most common programming constructs, because they actually work in a logical way exactly as they work on different programming languages. So for instance, the if programming construct, of course, it's a logical construct to define which lines of code to run. So it is the if construct is defined by the keyword if. So if name of the variable and then logical evaluation and the number. So in this case, altitude is a floating point number, and I'm considering if it is greater or equal to the number 3000. If this is the case, so if this is true, the statements inside the construct are run, otherwise they're not. So in this case, altitude equals 20. What happens is the first evaluation is done on the variable altitude to check whether the statement is true or not. In this case, it's not true. So the second if called else if is evaluated. Else if is basically the way to tell MATLAB, okay, if this is not true, then check this condition. If it's not true, keep checking. So else if check other condition, or check other condition. Of course, this can be done with an arbitrary number of conditions checked. So, of course, what happens is when the conditions are not met, the lines inside the construct are not run. The only peculiarity of this command is that the last condition, let's say the general condition, must be called as else. So when we call for the else construct, we don't give any statement to evaluate, because it's the most general case. So every else if is checked for a value. If none of these evaluations are true, then the following lines will be run by the command. So you can see it can be a very general programming construct. Let's say that worst case scenario, we don't want our program to do anything if these conditions are not met, so we can just give else without any line of code. And so if no conditions are met, the program will just skip through all of this and end this construct and keep work, and the rest of the code will keep running. Yeah, this is just an example. For instance, this where the string danger is displayed to the user if this condition in a logical way is true. Otherwise, I mean, in any other case other than this, only OK is displayed. Okay, an example on recursive functions, which is maybe a little bit too advanced for today, but still, how can we define a function that calls itself actually? Let's see the general definition of this function. So function keyword output equal name of the function and then the input, and then inside we find the constructs of the function that are run when you call the function. So in this case there is a logical condition. So if n is equal to 1, or the two lines are the logical OR operator. So if n is equal to 1 or n is equal to 2, the output f is equal to 1. So as you can see from the theory of the Fibonacci sequence. Else, so in any other case other than n equals to 1 or n equals to 2, f must be equal to the sum of these two values. So what is happening here is actually f is the Fibonacci function keeps calling itself by changing the input, so n-1 and n-2, until of course it reaches an input of 1 and 2, where f will become 1 and all other functions will be evaluated. So apart from the, let's say, computational complexity of the functions, this was only to show you the if-else command to see how they are implemented into a function. The most simple way of doing working with programming constructs is the switch case scenario. The switch case program is the most simple way of programming, because it simply considers a variable and evaluates it, and according to its value will output a result. So in this case, the switch case is implemented as switch and passing it the variable we want to, let's say, switch on, and then cases, the command case, to evaluate all the possible cases of our function. So in this case, I'm considering, I'm working on the variable n, and so this is basically if n is equal to -1, run this code. If n is equal to 0, run this code. If n is equal to 1, run this code. If no cases are checked, run these other lines of code. So, as you can see from what I've said in a direct way, the switch case programming construct can be changed with the if construct, but of course this is a more let's say a faster and a simpler way to implement a programming construct. Of course, it's simpler, but let's say less elegant when programming. But of course, it's robust and still would work for simple algorithms. Then the for and while loops. Of course, loops are present in every kind of programming. The for loop is implemented as follows. So the for loop is implemented as an index, which must be equal to the first element to consider, the increment to have, and the last element to consider. Let's make a simple actually the example is down here. So for index equal to first element, no increment is given, so it's automatically considered as 1, and then the last element. So for each increment of v from 0 to 5, I want to display, to show the value of v. So by running this code, what I obtain is v equals to 0, 1, 2, 3, 4, and 5. So it's actually very straightforward. Of course, inside of here, I can put any statement I want, any command I want. Of course, to run conditional programming. Another loop, which is actually is the same as the for loop, just implemented in a different manner, is the while condition, the while loop. So the while is implemented as, of course, the keyword while, and then the conditions. The condition that needs to be true to run the code lines inside the loop. I should have, yes, I got one here. So for instance, I'm considering a variable called n, which is equal to 5, and I'm putting it inside of a while loop evaluation. So while n is greater or equal to 0, I want to display n, and then each cycle, each loop, I want to reduce n by 1. So what is happening is that by displaying n, I see that it starts from 5, and then it keeps reducing by 1 until it reaches 0. When then this condition is not true anymore, and the loop is closed. If I put let's say the change of n before the display, of course I see that it is changed before the display. So while in the for loop the index is changed automatically each iteration, in the while loop this doesn't happen. So it must be considered inside of the code, inside of the loop. So yeah, this is an example with logical analysis. Actually, we're a bit out of time, so I'm just going to skip this. Of course, actually, if you want, actually, I'll tell you later. But still, if you want to see in a more detail these scripts, you can get in touch with us, and we can send them to you to see actually to keep an example of programming with you. But still, I wanted to show you the most important part about the programming. So the fact that the variables and the parameters that are in the functions are local. Some of you might have experience from, for instance, C++ programming with global variables and local variables, where variables can only be seen by certain functions and not used in other algorithms. This is the same that happens with the function, which is actually why we use them a lot, because each function, whether they are in the same script file or in a different file, every function has a local workspace where all the operations that are done inside of the function are stored, and then they are cleared when you go back to your main script. So this is maybe should be bigger. This is actually a very clear example of what is happening when you call for functions. So in this case, in my script, I'm creating a variable, and then I'm passing it to a function called foo. So what is happening here is that the value of my variable 42 is passed to the environment of the function. So as the function was defined as y equals foo of x, in my let's say in my local environment, the value of a is passed to the value of x. So in my local workspace, we wouldn't see a, but we would see x, because it helps. It's required for MATLAB to compute the function. So all the operations are done, and the result y is a times b. So a times b is here evaluated as 0.723, and so this value is then passed as the result of my computation. So these two are the workspaces we have in MATLAB. Actually, this is the workspace we have in MATLAB because we're creating a and then passing it to the function foo. So the result will be only the variables a and b that we have as a result of our operations. What is happening inside of the function foo is that it's a local workspace which we cannot see, and we cannot operate on unless we apply some specific commands to make these variables global. But this is let's say advanced programming for future events. These variables we cannot operate on, and we can't see them, and they are cleared once we go back to our script. So this allows us to use functions and avoid having an overwhelming workspace, but also avoid using all of the RAM of MATLAB, because of course actually during these examples we only see simple arrays or matrices, but for instance in signal analysis, if you have a high sampling rate and long sampling times, we can have, for instance, arrays that contain like millions of elements and take up gigabytes of hardware memory. So actually it's very useful for let's say for real life scientific experiments. Okay, this actually says the same thing that we just said, so that the functions work, let's say, internally, and the result is much more clearer and simpler without using all the commands alone. And then we can conclude by talking about the function handles, which is a way of defining, let's say, built-in functions without the requirement of an input straight away. So we've seen before, for instance, that we can consider the built-in function sign and pass it and evaluating it point by point by giving it an input vector. This can be avoided by using the function handles, for instance, using this symbol, which Andrea can help you recall how it's called, because I can't remember right now. But still, what happens is, by inputting a function this way, we can then evaluate it later by inputting the vectors we want. I should have, yes, a much clearer example down here. So in this case, I'm creating a function handle called f. Function handle called f, which depends on the variables x and y, and then I define my function. So in this case, if I run this, I can see, I should see, yes, that f is saved in the workspace as a function handle with value my function, and Matlab knows that the dependency is on the variable x and on the variable y. So if later I pass to the function some values, for instance 0 and 0, Matlab automatically substitutes these values to the x and to the y of my function, and so I can evaluate the function how I prefer. Of course, instead of single numbers, I can also pass vectors, for instance, for plotting, and it's a pretty much straightforward way of defining function handles. Function handles are actually, I like to work with function handles a lot because they allow me to create objects inside of my script, inside of my Matlab environment, without the requirement to rely on different files. Because if I don't work with function handles inside my files, I need to create a different files when where my function is defined externally. So, okay, I guess this concludes our presentation. Unfortunately, I wasn't very much on time, but still, so I needed to skip some of the examples. But still, I hope it was clear to you about the theory behind the commands we used. On a side note, I wanted to take just 1 minute of your time to show you the other resources that MathWorks has got available for students. So I guess what is Matlab is now you know what is Matlab, so I don't need to repeat it to you. So Matlab is used by a lot of businesses, etc., etc. But what we seen today and last time was the, let's say, local version of the Matlab Onramp Matlab Onramp course, which is available on Matlab Academy. So Matlab Onramp is a course to, let's say, a crash course on Matlab to learn its basics. Today we've seen, let's say, the theory behind it, but of course you can also see it on the website. the MATLAB Onramp on the website is much more practical because it requires you to apply what you've seen from us in these days, to do some very simple and short exercises. And actually, let's say the most interesting part about the MATLAB Onramp is that after learning what was shown to you, if you complete it, you can complete it in any time you want. There are no time restraints. You obtain a completion certificate that you can obtain and show and keep on your resume. So the MATLAB Onramp is available on MATLAB Academy. You need to log in with your MathWorks account, but you've got one to download the program. And then, additionally to the MATLAB Onramp, there are more advanced programming courses like the MATLAB Programming Techniques or MATLAB for Data Processing Visualization. Also, for the bravest of you, the course on solving ODEs with MATLAB. And these are the additional resources you can have on the MATLAB website. Of course, actually, I was also told that last month more courses were added to the MATLAB Academy to teach students about data science, machine learning, and artificial intelligence. So I checked them out if I were you. Okay, let's go back to our faces for one last to say our goodbyes after today. So, Andrea, you want to add something about our presentation, our event?
I think you said everything, I think, but I just want to remember to the winners that you must contact us to have your gift sent, and I think that's it. So see you in the following events, like maybe the Symbolic events at the end of November, and of course another plot party in the middle of December with an incredible contest.
Yeah, of course.
Is right?
We've got a lot on our plate, so we will see you for the next events and contests.
Yes, of course, yeah. So thank you very much, and see you then, guys.
Okay. Have a nice weekend. Bye, everyone.
Bye, everyone.